We proceed to the next speaker. The third speaker is Dr. Majed Alrefae, who is one of the first graduate from KAUST. It was a decade ago. He then got experience with SABIC and then got his Ph.D. degree at Purdue University. Today, Dr. Majed Alrefae is an assistant professor at Yanbu Industrial College, which is just 2 hours away from KAUST. And his presentation will take us to the journey from the interface of a single fiber to the scalable technology, which could enable the mass production of a novel and tougher fiber-reinforced polymer materials. Please enjoy the presentation of Majed Alrefae.
Good day, everyone. My name is Majed Alrefae, and today I will talk about the scalable deposition of graphene nanopetals on carbon fiber. This talk is part of the Shaping the Future with Composite Materials conference organized by KAUST. The addition of graphene and carbon nanotube fillers to composite materials has been considered in the past 2 decades to improve the overall composite properties, including strength increase, weight reduction, and thermal and electrical conductivities enhancement. However, the preparation of such composites involve dispersion and inhomogeneous mixing that hinder the potential applications of such advanced materials because of the poor interfacial connections between the nanofillers and the composites. Therefore, several approaches have been suggested to improve the preparation of the nanomaterials-based composites, including the production of continuous carbon nanotube or graphene fibers. Today, I will talk about one approach, which is to directly grow graphene vertically on carbon fiber. Unlike the growth of carbon nanotube, which requires a catalyst layer, graphene grows seamlessly from the single carbon fiber as shown in this same image. These vertically aligned graphene sheets have a width of less than 1 nanometer, which corresponds to few layer graphene. This form of carbon nanostructure was discovered in 1996, and it's called carbon nanowall vertical graphene or graphene nanopetals. The unique nanostructure of vertical graphene allows for its use in composites by increasing the surface area, enhancing the out-of-plane mechanical properties, and improving the electrical and thermal conductivities of composites. For example, vertical graphene improves the interfacial shear strength and reduces the thermal interface resistance in carbon fiber composites as reported by these 2 studies. Although vertical graphene or graphene nanopetals have been demonstrated for several applications, the mass production of these carbon nanostructures hinders their adoption in the existing industry. Therefore, a roll-to-roll plasma chemical vapor deposition system was custom designed for large-scale vertical graphene deposition. The carbon fiber toe is placed in the top roll, passes through the plasma region, and finally collected in the bottom driving roll. Voltage is applied to the 2 parallel electrodes to ionize the gas and form a capacitively coupled discharge at a frequency of 80 kilohertz as shown in this image. Vertical graphene is deposited in the plasma region because of high plasma gas temperature and abundant active carbon species that accelerate the deposition process. The system has 8 input parameters that can be tuned for vertical graphene deposition. These parameters include gas pressure, plasma power, the growth time, and gas mixture of methane, hydrogen, argon, nitrogen, and oxygen. We implemented a design of experiment approach to optimize vertical graphene deposition to reduce the manufacturing cost and time by selecting the most likely operating conditions which can yield high quality graphene. In our design of experiment, we wanted to optimize 2 objectives. First, minimize the electrical resistance, and second, increase the capacitance of the composites because we intended to use the composite for supercapacitor applications. The electrical resistance was measured using a 4-wire Kelvin method, whereas the capacitance was measured using 3-electrode electrochemical cyclic voltammetry. We selected these 2 objectives because they can quantify the density and morphology of vertical graphene at reduced characterization cost. The results show that the electrical resistance was minimized at high gas pressure and high gas temperature in the vacuum chamber. The capacitance was found to maximize using a high concentration of nitrogen. The production time, which has an important production factor, has an optimum value of around 15 minutes, after which the capacitance decreases due to possible etching of vertical graphene at longer duration. We selected the optimal condition from the optimization process and demonstrated vertical graphene deposition in a roll-to-roll fashion for a 1 meter long carbon fiber tow. We measured the electrical resistance and capacitance for several segments through the 1 meter sample. The electrical resistance starts to decline in the second half of the sample, indicating a higher deposition of vertical graphene. Similarly, the capacitance starts to increase in the second half of the sample, in agreement with the electrical resistance measurements. The changes of electrical resistance and capacitance along the 1 meter sample can be correlated to the microscale structure of the segments, as shown in the SM images here. Initially, light deposition of vertical graphene takes place, followed by moderate coverage of vertical graphene, and finally, in the second half, abundant deposition of vertical nanopetals occurs. The trends in SM images explain the evolution of the electrical resistance and capacitance along the tow. The improved properties in the second half of the sample are due to the well-structured growth of vertical graphene. The observed changes of the properties of graphene-coated carbon fiber along the tow are related to the increase of the gas temperature in the vacuum chamber, as shown here. This temperature is for the gas temperature outside the plasma region, and it indicates a warm-up period in the first half of the production time. So, light to medium coverage of vertical graphene deposition on carbon fiber occurs in the first half of the tow, as discussed in the previous slides. When the temperature stabilizes in the second half of the production run, uniform and abundant deposition of vertical graphene occurs. The input parameters remain constant during the production process. However, the gas temperature increases due to natural convection in the vacuum chamber driven by the high temperature plasma. Therefore, the thermal characterization of carbon fiber tow during the roll-to-roll process is essential to control and optimize vertical graphene deposition, which is discussed next. Here, we developed a one-dimensional heat transfer model along the tow length, considering a 1 meter long carbon fiber tow. The substrate was divided into 3 regions: pre-plasma region, plasma region, and post-plasma region. Each region has its convective heat transfer coefficient and gas temperature, which was measured during the experiment. We developed a numerical model considering convective and radiative heat transfer from the tow to the gas and the chamber wall, respectively. Also, conduction and advection in the tow were included in the model. The carbon fiber tow consists of a few thousand individual fibers, which makes it challenging to model these single fibers individually. Instead, these single fibers are lumped into a tow, which can be modeled much easier. The tow was under tension during the roll-to-roll process, causing the tow to flatten out with an approximate rectangular shape. The cross-sectional dimension of the tow is around 1 millimeter by 2 millimeter, which was measured while applying tension in the roll-to-roll setup. So the temperature distribution was solved numerically in MATLAB. The numerical model was benchmarked with the analytical model as reported in our previous work. The temperature distribution was validated with in situ temperature measurements, which were measured with optical emission spectroscopy. For example, the emission spectrum was measured in the substrate vicinity with and without copper foil in our previous work. When copper substrate was not included in the plasma, the baseline remains flat with emission from plasma species. However, the spectrum, when copper foil was included, has an increased baseline, which corresponds to the emission from copper surface and contribution also from plasma species. The baseline can be fitted with Planck's distribution to infer the substrate temperature during the roll-to-roll process. The emission spectra in the vicinity of carbon fiber tow during graphene growth are shown here. The emission baseline changes with the tow position in the plasma region as presented in this image. For instance, the temperature in this plasma center line is expected to be high. Therefore, the emission from the tow surface is high. However, the temperature near the plasma edge is expected to be low. Therefore, the emission is minimized. Note that the tow was heated directly by the plasma without applying a supplemental heating, which reduces the production cost. The temperature profile of carbon fiber tow during the roll-to-roll deposition of graphene is shown here. The input parameters to the model include the properties of carbon fiber, which were taken from the manufacturer data sheet. The gas temperature in the vacuum was measured by a thermocouple. This value was used to represent the temperature in the pre-plasma region and plasma region, and post-plasma region, rather, sorry. The gas temperature in the plasma region was estimated from the emission of hydrogen, which was measured using optical emission spectroscopy. The effective heat transfer coefficient and effective emissivity from the tow were used as fittings to the model, as shown in this figure. The tow temperature increases gradually in the pre-plasma region, maximizes in the plasma region, and finally decreases in the post-plasma region. The temperature is high in the plasma region because of the high plasma gas temperature. Heat is conducted from the high temperature region to the lower regions, to the lower temperature regions, until the tow temperature equilibrates with the gas temperature in the vacuum chamber. The temperature profile in the three regions evolved with increased whip speed because of the heat advection by the moving tow. The temperature decreases in the pre-plasma region, plasma region, but it increases in the post-plasma region. Most importantly, the uniformity of temperature in the plasma region was reduced with increased whip speed. The changes in temperature profile results from the increased Piclet number with increased whip speed. Piclet number indicates the ratio of heat transferred by advection and conduction processes. At higher whip speed, Piclet number is large, which suggests higher heat transfer by advection. Therefore, vertical graphene deposition on carbon fiber is limited to lower whip speeds at which the residence time is long and the temperature is high. This would suggest that the throughput of graphene deposition on carbon fiber tow can be increased when the plasma region is enlarged. Also, the production rate can be increased by processing multiple tows simultaneously using a wider plasma. Finally, it's important to independently control the temperature in the pre-plasma region and post-plasma region to allow carbon fiber tow annealing before graphene deposition and cooling after the graphene deposition. Graphene nanopetals can also be deposited in larger scale using a batch process. This process accounts for most, if not all, published reports of vertical graphene or graphene nanopetals. The deposition is more controllable in this process, which can take from around 30 minutes to a few hours, depending on the plasma source and the process conditions, to produce vertical graphene in large area substrates, as shown in this work, which was reported by Wu et al. They showed that vertical graphene can be deposited in large scale with different sizes. The main parameter to have high quality graphene at large area is to have a stable plasma and have a uniform substrate temperature, which can be heated by the plasma or supplementally using a heater. Carbon nanostructures such as graphene and carbon nanotube possess excellent properties that benefit and advance current technologies in composites. However, the production cost of these nanomaterials must be reduced to replace existing materials. Similar trends have been absorbed in other materials such as silicon, carbon fiber, and polyethylene, which had an incubation period for a few decades. The demand side of graphene must be realized in applications that demonstrate their benefits compared to their alternatives. I think carbon nanostructures, and mainly graphene, can be first commercialized in composites applications. In addition, graphene properties should have a high repeatability between sample to sample or batch to batch to meet quality control measures. The same should be applied for properties uniformity across the sample to avoid hotspots. The uniformity and repeatability can be checked using high throughput characterization tools at a lower cost. These challenges can be overcome by establishing a strong collaboration between universities and industries. I think the establishment of the Saudi Arabia Society for Composite Materials by Professor Gilles Lebonneau is an important step for such collaboration. I would like to thank my advisor, Professor Tim Fisher, and my colleague, Dr. Kim Saviors, to work on the roll-to-roll production of graphene nanopetals on carbon fiber. Thanks to the staff at Burke Nanotechnology Center at the Discovery Park of Purdue University for their support. We appreciate the financial support from the National Science Foundation through the Scalable Nanomanufacturing Program. Thanks a lot to Professor Gilles Lebonneau and the organizing committee members for organizing the Future Composite workshop at KAUST. Thanks a lot for joining this talk. Please let me know if you have any question. Thank you.
Yeah, thank you very much, Dr. Alrefae. We are looking forward to hear some questions to your presentation, which was very deep and informative. Thank you very much. It was quite a lot of nitty-gritty, but now we know better the CVD process. Yeah, and the first question is from Professor Pedro da Costa, who is the next speaker after. That's why he's very interested. It seems like his project is very related to you. Professor Pedro da Costa.
Thank you. So it's actually, as you said, for me, it's very interesting because it's a perfect adoption of the plasma enhanced CVD. One thing that I wanted to ask, Majed, does it make difference the type of fiber that you use? Because you have this, I assume it's continuous fibers, pen-based fibers. When you use, for instance, these graphitizable, more graphitizable fibers, like the pitch ones, they tend to be more rugged edges, like hexagonal shaped, isn't it? More graphitized. Would that make a difference for the growth rate or density? What do you think would be? Does the surface of the fiber matter?
Thanks, Pedro. I think it is a good question. In my opinion, I think the control for the deposition rate and the shape and structure of the vertical graphene is mainly driven by the process parameters, such as pressure or plasma power or the gas. If we look into the growth mechanism for vertical graphene, it's actually in the beginning there will be a horizontal few layer graphene deposition on the substrate. So either using any kind of fiber material or even metallic material. So usually there is a carbon fiber layer deposition, and then from there, because of the plasma, there will be vertically aligned graphene deposition in there. So I think the substrate will have, it will have minimum effect on the growth rate and the morphology. However, I'm talking about the substrate, for example, from carbon fiber type to other type, or from, for example, metal copper foil, for example. However, there are some substrate, for example, they will not allow for vertical graphene deposition, and that mainly depends on the structure itself. So, for example, for nickel, for example, usually it's a little bit difficult to have vertical graphene deposition because of the solubility of carbon is high. So I think that's in your talk. So carbon, instead of growing on the surface, it will just dissolve in nickel.
Okay.
Yeah. Okay.
Majed, the question from one of the attendees, how good is the adhesion of the vertical graphene on these fibers?
We haven't measured the adhesion properties on the like to have formal values to do. However, from experience that we handle the fiber, we do the testing and we do SAM. It's really strong and really adheres on the substrate.
Thank you.
Yeah.
Going closer to industry, could you please elaborate this scalability question of CVD process? As I understand, we need not just the one small piece of fiber, but we need 1,000 of kilometers of these fibers. How it can be scaled for the industrial demand?
Yeah, there's also an excellent question, and this is actually the purpose of the work, right? So our work is actually at the beginning of scaling up this process. I think and the excellent presentation by Celine explained this. For example, instead of using one carbon fiber, you can use 8 or 10 together so that you can increase the production rate. Also, you need to use a long carbon fiber facility, for example, carbonization and also for the vertical graphene deposition. Yeah, I think the main factor is to control the temperature. Once you have high temperature in the plasma for a fairly long, then that can be achievable.
Looking forward, hopefully. What about the diameter of these fibers? Does it affect the growth of the vertical graphene?
I think it has minimum effect as well. However, we have preliminary results that show reducing the diameter of the fiber does actually affect the growth by increasing the deposition rate and also enhancing the morphology. And the reason for this is because of the enhanced, that's what we're thinking is because of enhanced electric field around shorter, around smaller fiber. So that's one reason. Probably also we are thinking, and that's still we are trying to model it. That's also maybe because of the if you reduce the diameter of the fiber, that probably will increase the temperature, lower mass. So that probably increase the temperature, and therefore maybe that will increase the growth rate. So the answer is the reducing the diameter of the fiber does increase the deposition rate. Yes.
So it's proportional.
It's inversely.
Sorry. Yes, it's inverse. Thank you. Yeah, returning to the work of Celine Largo, we've seen that the FORCE project is targeting to get 1 kg of carbon fibers, bio-basic carbon fibers, for €8 per kg. As we understand, your carbon fibers will be of completely different price range. What's the application domain for these fibers which you're working on?
So basically, when we started the project, we planned to use it for supercapacitor applications, energy storage, because when you deposit vertical graphene on carbon fiber, for example, or composite material, that will increase the surface area, and therefore the increase the capacitance of the and the energy storage for that. Other applications, for example, if you look into composite, particularly in composites, is to reduce the interfacial resistance, electrical resistance between the composite and the resin, for example, as well as the thermal resistance, right? Because you have more contact for the electron or photon transport or between the fiber and yeah, I think. I think it has many applications. Like it's been written in review papers ranging space applications to biosensing, among others.
Thank you.